Okay, good morning, everyone. Let's start. Okay. So today mainly I'm going to start talking about introduction to target tracking. I may repeat some. Sean already did something because our language could be different, so that way so you can understand better when I talk about more on the later on, right? So just to start target tracking, I would just play a video to show that what we really mean by tracking. Right? So if you look at this, this is actual real data from a self-driving car. So this is LiDAR. So if it's a radar, similar but like less dense data. Okay. So in this case, the green dots are the detection, or we call it a measurement, from which we want to extract tracks. That is our objective. Okay. So objective is to identify the car, right? So if you think about self-driving car, we want to track the vehicles around us before we make any decision. Okay. So in this case, our detections are the LiDAR returns, and the red ones are the tracks that we produce. Then the tracks will go into the high level decision making where you want to decide whether you want to brake or not. Right? So in this course, what we are going to do is, for us, the input is the green dots. Right? When we talk about tracking, LiDAR gives detection. Even before you come to the detection, there are a few steps, right? So it generates the raw data. From that, you want to get the detections. That usually we use called CFAR, right? Concept Force Rate, to generate the detection. Then we do the tracking. So in this course, we assume that the detection part is already done. Okay, so that means somebody give you the green dots. So you are going to develop an algorithm that will give that red boxes or traps. That is the multi-target tracking problem, right? So if you look at only this output, right? So what are the problems that we see? That is why we always have some research areas to work on, right? If our output is perfect, then we don't need the research direct, right? If you look at that, this one, it's reported as a car over there, but that's not actual car, right? So that is some surrounding. That is called false tracks. So we'll talk about that. So this is a false track reported by the tracker. So our objective is to reduce that false tracks, right? So this is also. And sometimes we want to do classification, but in this course, I not only talk about because we don't have much time to do talk about classification. So sometimes we want to identify the type of the object. This is a car, this is a pedestrian, right? If it's a camera, you can easily say by looking at it, but with the radar and LiDAR type of sensors, little hard. Okay. Anyway, so the objective is tracking the objects using the measurement. Okay, that's the multi-target tracking problem. And so if you write a paper, sometimes we assume the number of target is known, we want to do the tracking. But in the real world, that is not the case. Nobody is not going to give you that. Okay, we have this many targets. That is not known. Nothing is known. Only thing that you know is if you remove all the red, that green. That's all is given to you. Then up to you to come up with how many targets are there, and also time varied. It's not fixed. Every time the number of objects in that scenario vary. Right? That's not known to you. You have to estimate that also from the data. That is where the tracking comes. I think like yesterday and today, maybe you were talking about single target tracking or Kalman filtering. Filtering is one part of tracking. Tracking comes when we want to estimate the number of tracks and terminate and so on. We will talk about it. Okay, that is the general idea of tracking. So let's start with target tracking. First, I will introduce some terminology so that whenever I talk something, so you can understand what I'm talking about, right? The first one is the target. So because target tracking, so target is the one that we want to find out. Usually in our application, most of the time, target is the one that moves. Usually moves. That's not perfectly correct, but technically, like if you think about self-driving car, we don't track parked cars. That's kind of a little challenging or different problem. So we want to track moving cars on the road. Okay. So usually when we talk about targets, we talk about the actual object that moves. Okay, tracking is finding the states of moving objects using the sense. Okay, so whenever we say target, that is what we want to estimate or track. Okay, and the other one is the measurement. Sometimes people call it as detection, and sometimes we call it like real world people call it as clutter. Like when you talk to different people, because when we talk to our at least different people, when they say measurement, sometimes they don't understand, right? They will use the term plot. So that people will use these terms interchangeably, but they mean the same.
How the plot work?
Wow.
How the plot works with the intention?
Okay.
Some very times the plot. So why the terminology attributed to predictions?
I don't know. Maybe like the defense people, I think when they doing the plotting and they put the detection. I don't know the exact reason why they call it. I never use plot. I use measurement and detection, but some of the defense people use the term plot. Maybe the historical reason they use it, right? So, but usually uh, in the papers you will read as measurement or detection, right? So that's the other one is the false alarm clutter. For an example, if you go to this video, so we can consider this as false alarm or clutter. We are not interested in it coming from trees and ground and so on. That's called clutter. And these are the actual detection from the car. Okay, so that is what we use. Then the and scan. If you study Karnavit already, Remo scan is K, capital K. We talk about capital K, right? But again, it's also like a little harder for the people, real world people. Frame usually means camera. For example, if you're a camera, then you can call it as frame. Scan usually used for rotating radar. If the radar rotates, then we use the term scanning. Right? So, but like in the paper, we use frame all the time, right? But the frame could be for phase the radar for an image. And okay, just to simplify this, whenever I think we talk about Kalman filter or even my course in target tracking today, we are going to assume the measurements are going to come in a discrete time. Like it comes here, 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 and say this is time. And we say k equal to 1, k equal to 2, and so on. This is what we achieve, right? So the measurements come at this time, and this time, and the sampling time or the time difference between this to our capital T. Okay, so that could be 2 seconds, whatever it is. So that is what we assume. But in real world, if you are rotating radar, the measurements will come from everywhere, like these. So it's rotating, right? So whenever it rotates, it collects the measurement. So that means there is no definite time in which you get all the collection of measurement. These are the challenging and advanced things. So I know we are not going to focus on that. Mostly we are going to talk mostly about frame rather than the scan in which you have different rotating time. If anybody is interested in that, we can discuss after the class because that will make the problem a little harder. Okay. So, but in this case, we mean the frame or the scan, the whole duration. One scan it takes, how much time it takes for one scan. Okay. The frame or scan is used to say that the number of measurements come from one rotation or one snapshot. For the LiDAR data for the autonomous vehicle, that is like a frame because in that they get all the detection at the same time, wait some time, then get the detection again. That you can consider like a frame. But if it's a military radars, usually that rotates, that is like a scan. Okay. And then we are going to talk about track. That is the main thing that we want to discuss, right? So when we talk about track, say if you have a scenario like X and that's the coordinate, let's say this is the actual target goes here. There are two targets here, one over here and one over there. So we want to do the tracking, and you may get something like that. Right? Red is the estimate that we get. Black is the actual target. In this case, so I'm tracking this, I'm tracking that, and that's a 4 track. Right? So I have, instead of 2 targets, I have 3 tracks. So when we talk about tracks, let's say you consider a structure. Say you want to save the track in a data structure. Okay. Say assume that's a structure with certain fields. How many fields that you can think about? Anybody? Can you mention one? Like there are a few things that we are going to fill. Can you start with one of them? Say I will start one. Okay. ID. So I say this is 1, 2, and 3. So each track we will assign an ID. Okay. So that is the first step. Anything else? Anyone else? You know anything about tracking or filtering? Position, right? So position, yes, you can call it as position. I would call it a state, right? Instead of position, I would call it as what else? Pardon?
Velocity.
Okay, velocity, yeah, that's right. The state, I would call that as position and velocity included in the state, right? That could be. But yeah, that's covariance matrix, right? Covariance is important, right? That's right. So that is the next one. Status, I think I will spend more time on the status part. Okay, status means whenever we create a track, immediately we are not going to display to the user. Okay, so we will wait some time to confirm that. So for example, like I will talk about that later, but just to give an idea of what is status. I think that this is the first frame. Okay, this is the first frame. K equal to 1. You have 2 measurements. I asked you how many tracks are there? How many actual targets are there? What can you say? We cannot say that, but say if you want to give some estimates, okay, what are the possible values? 2. What are the other possible values?
Everyone.
1. It could be 0. It could be 1. It could be 2. Can it be 3?
Yes.
It can be, right? So any number is possible. But the best thing that we can do say that, okay, there's 2 tracks here and there. But how certain that there are 2 tracks? You can't say much about at this time, right? So that means if you want to break a car, right? So you don't want to break based on these 2. So we would wait, but in this case, we would assign this as tentative. Tentative is only for tracker, not for the user. Assume that somebody is using a tracker developed by me. So tentative is for internally. Outside, I say that no track is at this point. Okay? And when you go to k equal to 2, then you have one more track C, one more measurement here, and say this is a second measurement. Okay? So I'm going to say there's a second measurement here and the other measurement here. Now what do you take? By looking at this, now we have a 2 measurement from 2 different frames. The first frame we have here and here. The second frame we have here and there. So now you have a little more information about what's happening, right? Say now if I ask how many tracks are actually there, what would you say? Well, most likely you can say that this is an actual target. This could be a false alarm, but still we can't decide. Maybe we will wait a little longer and decide, right? Anyway, we'll talk about that. At least, like at this point, you know that it's confirmed. Maybe like so, I would say that. Okay, this is confirmed. That is a status. For each track, we will say what is the status of that track. Correct? Okay, later on, like we may add additional attributes here, but for now, these are the ID, state, covariant, and data. These are good enough to start with. Okay. I'm always really concerned about the time because at McMaster we teach this course and every lecture is 3 hours. We have only 2 hours, but I go in the same rate I would do at McMaster. But let's see. I will finish as much as I can. Okay. So then, okay, track, we already talked about that, right? So process noise. I think you have already studied in the study. What is process noise? Pardon?
Model anomalies. Model anomalies.
Modal anomalies. Yes, that's right. Right. So this will be going with a quick question, maybe, right? So process noise is the one that you use in the model. Anyway, I'm going to talk about the model. I think you already studied about that. Noise is the uncertainty in the prediction of a target. So you can call that as it. And clean scenario. So clean scenario, that's no actual thing, but like clean scenario, whenever we say clean scenario, no false alarm, failure detection is one. That is, I would call as clean scenario. Okay. PD is one. We'll use lambda later on, false alarm 0. That, so whenever you develop a tracker, I always tell my students, test your code with a clean scenario. Clean scenario means ideal scenario that you can get. If your tracker doesn't work in a clean scenario, it's not going to work for them, right? So that's the starting point. Always, when you write the code, don't write the code for clean scenario. Write the code for general case, but when you start testing, set those to that and make sure that your tracker works. Then you change the PD values and lambda. Okay, so here PD is a probability detection of detecting the target, and lambda is the number of false alarms that we are going to. Okay. And the other thing is two things: state space and measurement space. I may use that very frequently. So these are like two coordinates, right? The state space usually x and y. It includes x dot and y dot, and it's kind of hard to plot 4 dimension. That is the state space. Measurement space is r and theta. And one example, right? So if the measurement is radar giving the range and azimuth, then this is called measurement space. That's the state space. Okay. Okay. So now when I just revise the concept, I will talk about which part is done in state space and which part is done in the measurement space. So, and then we do the data associations. We will do that in mostly in the measurement space. Okay. Okay, so with these terminologies, let's go into the tracking. So I don't want to spend too much time here because I already explained what is target tracking. So you estimate the number of tracks, their state, current state, right? Where they are. And these two are important. This is important, okay? So if you think about a track, so you would get X and P. There are cases in which we don't have P. Okay? For example, like these days, machine learning, even in my lab, I think towards machine learning, they use machine learning for tracking. Sometimes you may not get the covariance, or a little harder to get. Okay? But when we talk about track-to-track fusion and so on, this covariance is important. So whenever you give an estimate, always you give a certain, how certain you are about that. So the covariance should be attached to any estimate. For example, if you use a Google map and you use a GPS location, it will say that you are here But this is my answer, right? So that Google Maps at least says that you are somewhere in this region rather than saying there and that's wrong, right? So you should know your coordinate, right? So that is important. So when we talk about track, it has to be the estimate and the corresponding covariance that and number of tracks. So we want to decide how many tracks are there and so, right? And we should be able to predict the future state. That if you know Karl Marx, I think we can predict the state. Okay. So this flowchart, this one shows a general tracking system. So we are focusing making this course mainly on these two. Okay. This is the environment. So you have sensors, single sensor, multiple sensors, and this is signal processor where you do the CFAR detection or any way. Usually, so here you get some signal like this, and here you will get detections. So that I mark as that. This is the X hat. This is a P. Okay. So the sense arrays give the signal, and you do some thresholding and say there are one tag here and there or detection. Then that the measurement is going to be the input to our tracker, and the tracker will provide estimated states of all the tracks and the corresponding covariance. This is an optional one, right? So in most applications you may not have. Okay? But in some application, if you can manage the sensor, maybe the so in our objective is to always improve tracking. So you try to improve, but beyond certain value, you can't improve. I think you guys already talked about PCRE. I think you can. So PCRE is the one saying that if you use this sensor for this target, that's all you can do. Okay, say let's say with a PRE it says that the minimum error that you can get is 30 meters. But the customer says, I want to go to 20 meters. But with this system, you can't do much about that. But then the sensor manager comes in. Maybe you can change the sensor location, for an example. Okay, or the sensor has different beam patterns, something. So you can play with that to produce that CRI. So sensor management offline, online, and so on. Offline mean if you think about the self-driving car, so I give you a camera, I ask you to place a camera somewhere. That's the resource management problem. Sensor placement. You have to decide where to mount your camera on the windshield. So you will consider several factors to decide the optimal position to place. That's a simple way to see that. But in our case, usually we see we want to reduce the CRL over time. What is the best location that will give a better CRL? Okay, that is offline. Online means, say you want to track a car going on a road using an UAV or the drone or helicopter. In which case, how would you manage the trajectory of the helicopter such that you can have a better estimate of the weight? Okay, that is the online. For that, the input is the this is only for online. Okay, this is not offline. Online, you give that these are the estimated state and covariance. Then you decide where I need to move next time. Okay. Okay, major components in the tracking is the first one is the target, and also we call it as ground truth. Okay. So this one mostly be used in the simulation and also performance evaluation, evaluating how good your tracker is. But the tracker should not use that. If you are doing a simulation and if you generate the target, you don't use that. You can't use that in the tracker, or you don't pass this one to the tracker. But in order to say if you simulate it, as a first thing, what you do, you generate a ground truth. That is called ground truth, right? So actual target. Then you generate the measurement around it. Then pass it to the tracker. That gives the track. then you have the, maybe I would say MOP, measure of performance or performance evaluator, the end. Okay. That's the first thing, ground truth. And let's think about a few target types that we are interested in. That depend on different application. I think, I don't know what area that you are going to work on. But like say, one of them is aircraft, right? And for the autonomous vehicle, car, pedestrian, could be drone, could be missile. Okay. And if you think about biomedical engineering, then maybe cells inside the body that moves, you want to track that, right? So in the mining environments, you want to track the underground people or the vehicles in the mining. Those are tracked hard for you, right? So if it's a senior home, you want to mount a smart system in which you want to track the person on that senior home. That the person becomes a track. Okay. So depending on the application, target is different. And then the sensor. Sensor is the one we use for tracking. Mostly we work on radar for defense application. What are the other sensors? LiDAR, camera, sonar. There are several sensors, okay? Different type of sensors that you have. Can radar be a target? Yes. Under what condition radar can be a target?
Passive ground radar.
Ground radar, yeah, okay. So can you explain why that is a target?
For a missile to stop his center.
Okay, so radar can be a target. So for an example, say you have a radar 1, this is radar 2. Say this is yours and this is enemy's radar. Okay, so you have, this is your radar. So that is, for an example, into the aircraft or missile, whatever it is, that has a radar as well. For you, that is the target. So you track that aircraft. But for that person, as for your enemy, sometimes they want to know where your radar is. Right? There's so-called ESM. So in the ESM, what they do is they capture your radar returns and then you decide where you are. Sometimes that is why sometimes we like passive tracking in which enemy cannot find out where you are, right? So this is in one case radar can be a target for someone. Okay. And tracker, we already talked about that, or that is what we are going to talk about it. Sensor management, I already talked about that. Next one is the fusion. That is a little tricky terminology for fusion, I think. I will have a, maybe I'll talk about this and go back. When we talk about fusion, first of all, we said we have multiple sensors. Then only we are fusing information from multiple sensors. Okay, so in this case, we have multiple sensors. Each of them gives that, then do the fusion at this point. We call this as the fusion as well, but in that point, I consider fusion as the second case, but that's the terminology. Okay, so fusion is mean fusing information from multiple sensors together. In this case, this will provide tracks. Okay, this is called centralized fusion, in which sensors give the measurement, you fuse all the measurements and give the track. This is called distributed fusion. That is what I mainly meant on fusion there, in which what happens is that you have that and that and that here, then tracks and tracks, then you have track. Okay? What happens is that you fuse a measurement and get the tracks, fuse a measurement and track, then you want to fuse these two tracks to get the common track. So we have two kinds of fusion. Measurement level fusion, other one is a track level fusion. And the measurement level fusion means fusing the detection directly or fusing the tracks and get the track. Okay, that is what I meant here. Other one is a classifier. That means to classify the type of the target. We are not going to talk much about that. Okay? So here is one of the application of submarine tracking. So you see that this is a submarine. There are several submarines, and these are sonobuoys. Usually, sonobuoys are deployed from a helicopter or something, and they are like you use it and use for like 10 hours and score, right? And could be like $1,000, but then for defense application, that's not that much. But anyway, so you have some sonobuoys deployed anywhere, everywhere. You can consider this as a fusion node. Maybe you can consider this as a centralized fusion. These are like a local fusion nodes. They collect the sensor measurement, fuse the track, and send it here. That gives a global view of what's happening in that whole area. Okay, the sonobuoys could be active and passive as well. Okay, so this is one application of target tracking. And application of target tracking, when I started my PhD, mostly is about defense. At that time, mostly defense, but like last 10 years, it's mostly moved towards the self-driving cars, autonomous vehicle, and smart city, and so on, right? And some other areas like still you have some application, but the main two areas that I'm working on at least these two. Okay, and some other areas are like intelligent housing and senior homes, for example. Like I'm working with another student on using the lights to detect the person inside the room. Because the camera is a good option for self-driving, but the privacy is the big problem with the camera, right? So some people won't prefer to have a camera inside a room. So in that case, people try to use lights and radar to detect the people or the elderly people to detect. And okay, there are several applications. I don't want to talk too much about that. This one I already mentioned. Centralized fusion, distributed fusion. In one lecture, we will talk about track-to-track fusion, and mostly we will work on that. Okay. Again, I repeat that. So it's usually I spend like 10 times 3 hours to finish everything. So we are pushing as much as I can, then read, and that's why like try to get the overall idea rather than knowing exact minor details. That's hard, right? Even if we make the full course, it's kind of hard to know. As long as you get the high level idea, then you can go and read. Okay, the main thing is that you need to know at least, okay, you work on this problem, okay, you know that, okay, I heard about this is what I have to do, just follow. Okay. Decentralized, okay. Okay, distributed and decentralized. Okay, so decentralized means do you understand this part? In this case, distributed means in this okay, let's consider this, okay? Let's consider this in which these are sonobuoys, the white things, sonobuoys. Okay, these are sonobuoys, and that is there. And let's say these are local fusion nodes are like these shapes. And this is the, so this one should be, that is this, and this, right? So you can explain, right? So these are sensors, and they are connected to the fusion nodes, then that is the central step. Decentralized means there's no such thing as a global one. So that means there's nobody knows everything. So basically what they do is they have only communication between them, and from that somehow they have to get the whole view, but they are not directly connected to the whole system. Okay, so then when we don't have a global dash, if you cut it, that's the decentralized. That means you see that all the fusion sensors are connected to each other, but there's no one master one that connected to all. Okay. No, I can't say there's no global picture, or you can say that everyone has a global picture if you do some kind of optimal fusion. That's a harder problem, you see. But if you see that this connected to this, this connected to this, this connected to this, this connected to this, somehow the information is flowing everywhere. The harder part is a correlation, handling the correlation properly. But over time, with some, at least with some latency, you will get some information. This information might reach over there. So that way you can simply like, say that, okay, you will have some kind of overview, but it's not an easy test. Right? Okay, so this one I got to test because rather than teaching, I can test it because you already studied about that, right? So whenever we talk about tracking, whenever you work on a problem, any tracking problem, first thing that you need to decide is this. Okay? Yeah. So whenever we define a problem, you have to come up with these two equations. Any tracking system has to have it. Without this, you can't do any tracking. Is that clear? So this is called state equation. This is called measurement equation. Okay? So when we talk about the state, this is a vector contains maybe x, x dot y, y, for an example, one example of that, right? So I think you learned about it, right? So this is position in x coordinate, position in y coordinate, velocity in the x coordinate, velocity in the y coordinate. That is a state. This is an unknown. We are going to estimate. Anybody knows the difference between parameter estimation and state estimation? Or at least can you get from the name itself? What is the parameter estimation? What is the state estimation?
So basically, time static, state estimate is a time management.
Yeah, that's right. Could you expand a little bit?
State estimation is your estimating the agency.
Yeah, they're kind of similar. So the state I normally tracking considered as a state estimation problem, but it can be a parameter estimation problem as well. Parameter estimation means you don't know the state at this point. If you know at that point, if I ask what is x, k equal to 10, then let's assume the error in this one is 0. Okay, so you know the exact location at this time, then you can say this position exactly. That is called parameter estimation problem. Okay. Okay. Yeah. Okay. Yeah. So let's make a break and then we can.
Update is like six. The Farmers have the shares of the lecture notes, slides, and then we'll have that. Compared to that, this is just an updated one.
Okay.
That's not the answer.
That's what I.
It's a yeah, containing we can talk, but we have to digest that. But if you go back and we get it checked. And there's that day as well. Actually, for it. Yeah, we can do that.
Any questions so far?
To cover association.
Clear association?
Yeah, association.
Yeah, okay, this is my plan, right? Time. So like today we'll talk about this introduction to tracking, and tomorrow in the first half we will talk about the performance evaluation, how to evaluate the performance and so on. Then I will talk about at least how to do simple tracking, including track initialization, data association, and track management, right? But data is a huge topic. We will at least talk about the other. Yes. Yeah, I can introduce, but yeah. PDF we are not. Are we waiting for someone?
Yeah, so it's a bit too much enthusiastic, so they are asking if you want, you can extend this lecture hour.
Yeah, I'm happy to do that because so we can shorten that 2 hours to 1 hour, maybe the break time, right? Yeah. Okay, yeah, I'm happy. I'm happy because I want to make use of the time here. Okay, let's continue. Okay. First, I was talking about these parameter estimation problem. Because if the PhD students like do the comprehensive exam, there's an exam for that. Usually I will ask what is parameter estimation versus state estimation, right? The parameter estimation field, you don't know some parameters, but if you know the parameters, at this point, you can predict the state at any point without any error. That's called parameter estimation problem. State estimation problem is even if this is 0, this is not 0. You can't predict accurately. Okay. So that if you think about Carnot filter, if this part is not there, then you can consider it as a parameter estimation problem. There's no noise in that system. So if you know one location, you can predict the other location, right? So that is called the state distribution problem. Okay. Okay, then I was talking this. So whenever you are working on a problem, always start with that. You want to define these two. Which one is easy? I think you already studied Kalman filter. Kalman filter based on this, and this is a linear one. But I have written a normal, general nonlinear form. Okay. So out of these two, which one is easier? And if somebody work on that tracking and say, which one is easier? But again, I can define what is easier. You define what is easier for you, and then tell me which one is easier to define, this or that. I believe you know these two, right? This is defines how the measurement is generated. This one defines how the target is, right? Measurement. So this, yeah, at least for me, this is a straightforward. Okay. So that means if I give a same problem to two different students, this should be the same. But this can be different. Different students can have different thing of this for the same problem, but they can't have two different things this. Because this is decided by the sensor that you're using. If I say that the radar gives the measurement R and theta, then this equation is fixed. And this one says usually a Gaussian noise with 0 and R. Okay, measurement coefficient. So this part is fixed. This is a tricky part. Okay. That nobody knows. Like when we write papers, we don't consider this as a tricky part. But if you go to a real world people, or like if you want to process the real data, this is a tricky part. Okay. Okay, so the first thing that discussed here is the motion model. State equation and measurement equation both are needed. The measurement equation consider, as I mentioned, this is R and theta. This is the model that introduced the mapping with the state and the measurement. That's a noise. But this is a false alarm. Sometimes you get false alarm. So you will have some assumption about false alarm. False alarm usually we say is uniformly distributed. Right? I think in the today's afternoon tutorial, I think Showan will handle measurement generation for an example, right? So if you want to do that, see at a certain point, so you have two targets here and there. You ask to generate a measurement for this. Okay? How do you start thinking about generating a measurement for this? Right? As the first thing, you have to decide whether this one is detected or not, and this one is detected or not. How can you decide that? Like in the simulation. In the simulation, you want to decide this is detected or that is detected. How can you do that? For the measurement equation, I said that equal to hx plus this with some PD equal to 0.9. Otherwise, that's a false alarm with PD equal to 0.1. Right? So if the target is detected, I'm just saying only one target. This is not perfectly correct. Okay, I make a mistake. I can't say it this way because this is only for one target. This is not for target. Okay, this is not for target. So technically I'm wrong here. So this is for all the targets. Right? So I can't say it that way. Okay, so I will correct that. Okay, so this is wrong. This is wrong. Okay, this part is wrong. Let's leave that. Okay, so this is the correct. PD 0.9 you detect or not, right? So that means you generate a random number here. MATLAB you use a random, and if it's less than 0.9, you generate a measurement. Otherwise, you don't generate a measurement for that. Is that right? Okay, now this is known. This is known with the Gaussian distribution 0 and R, right? So what you do is you generate a random number here and put a measurement somewhere here based on the code. Right? And you go to this one. Hey, this is less than, it's not detected, so you don't generate any measurement for that. Those are generating the actual target measurement. In this case, there are two targets, I have only one measurement. We are done with that. Okay? Then the part I corrected is the number of folds is a Poisson distributed with lambda. Lambda is the one says that in the unit volume, how many detection that we are going to have. Okay? So if you know the total region, and then you say that we call it as lambda V and say that is 6.2. In this one, it says on average, you will get 6.2 detection as false alarm. Okay? So then what you do is you generate a Poisson random number from that. So that says, okay, 10. So you are going to generate 10 false alarms uniformly in the whole region. Okay, so the whole region is like that. You generate uniformly 10 detection somewhere here. Is that clear? That is how the not clear? Okay. So what is not clear? Okay, do you understand this part generating this measurement? No? You understood that part. So it's about the false alarm, right? Okay.
So this is term called probability of false alarm.
Okay, for the false alarms, you would define lambda. Say that is say 10⁻⁴, something like that. That is the average number of false alarm per unit volume or area. Okay. So for example, R and theta. Usually that should be in the measurement space. Okay, I will correct again. The measurement generation done in the measurement space, not in the state space. Okay. So assume the range is going from 0 to 10,000 and theta goes from -5 to pi. So this is the whole region. Are you okay with that? So now we have already decided with this lambda times this 10,000 times 10,000 times 2 pi is something like 6.2. Okay. So that this says that lambda says if you take a small area, this is the probability of having a measurement in that. That's a false measurement. But if you multiply it by the whole area, and you get 6.2, that says that on average you are going to have 6 false alarm in this whole region. But you are not going to generate 6.2 exact same number every frame. Okay, so this is Poisson random distributed. So that's the mean of that. Then you use the MATLAB Poisson number and generate that 6.2. That gives say for example 10. Okay, so now you have by this point you have decided you are going to generate 10 false alarm here. Is that clear? Now we want to decide how to use that, generate those 10 false alarms. To generate 10 false alarm, maybe the coding might be here. You only have 10 false alarm, right? So Ri and theta. Okay, that's all we have to find out. Ri is going to be what? 0 plus random number between say 0 to 1 times 10,000. I'm writing a pseudocode, not exact MATLAB code. Okay, so I'm writing a random number between 0 to 1, multiply by that, and you get a range random between those two. You do the same thing similarly here. -5 plus a random, I would say 0 to 2 pi. Okay, so you generate a random number 0 to 2 pi, then you add, so it gives a random between those two angles. That's it. So by doing that, you can generate This is R and theta. First you pick a point here and there, it comes here. Then you pick a point here and here, it comes here. Right? So you repeat it 10 times, you get 10 detection. This is only for simulation. The real data, it comes to you when you start working from there. Is that clear? Okay. Okay, that is this part. The measurement generation part is that. Now the state equation in which you have you decide how the target moves. So if you think about Kalman filter, this is the basic of Kalman filter. You need to know some kind of rate about how the target moves. Okay. I believe you guys talk about constant velocity model, is that it?
Yes.
Okay, so you know CV, right?
This morning only.
Okay, so you know about CV. You should know, right? Constant velocity model. Say, constant velocity model mean, and I observe you have to know about the dimension that you are talking about. Let's say you track the target in 2D. Okay, if you think about real world problem, when would you use 2D versus 3D? Anyone? Let's start with 3D. When do you use 3D when we do the real world tracking? Anyone?
Space and underwater.
Pardon?
Every space and underwater problem.
Okay, so you want to track planes and you want to track submarines. Okay, anything else? Right. In those cases, it's a 3D problem, right? So even the height is not known, and 3D. When would you use 2D? Car. Okay, car is one example. Anything else? Ship, for example, right? Ship is always on the water level. That could be 2D as well, right? And this goes like, let's focus on 2D because 3D is a little complicated. Let's focus on 2D, right? If it's 2D and CV, what is the size of this vector? If it is a 2D problem, CV, what is the size of that? 4y1. Okay, what are they? X, what is the next one? Velocity, y, y dot. If somebody writes this way, is it correct or wrong? Correct, right? So, but you have to change the F based on that, right? Which F to use, but that's what you have to have as a problem. Okay. But when it started, I said that this is the harder part to do it when you do the real world tracking. What is the remaining part? Okay, we decided this. So F is known, I think you know that F, right, for the constant velocity. This is a tricky part. What is it? That's a process noise. Again, a Gaussian noise with 0 and Q. That is a process noise. Usually, technically, you have to have some kind of G and V. Because if I want to talk about that, I can talk about that for half an hour about how to properly do that. Okay, anyway, so as a academic people, we don't consider that as a real problem because what we do is in the simulation, I assume a Q, then in the tracking, I use the same Q, and I say my karma works bad, that's optimal. Okay, now somebody give you the data, real world data. How would you decide the Q? I don't have the answer, okay, I'm just asking the question. How would you decide the Q? So I give the radar data, right? So I am just given the radar data. I'm not saying constant velocity model. So how do you decide whether you want to use constant velocity or constant acceleration or constant turn model? Those are the few models I have later on. But like from the name itself, at least, even if you don't know the equation, constant velocity means you are driving a car, actually constant speed, say you want to, I don't know the speed here, but it can drive 60 kilometer per hour. So you want to drive at 60 kilometer per hour. No one is perfect to keep it at 60. So it's going to be 59, 61, something like that. So that is a noise covariant, right? So the good driver, maybe I would say that the noise is like, if instead of 60, the person fluctuates between 60 to 62, noise is less. The bad driver, maybe there are so many bad drivers maybe. So it might be for 56 to 66, something like that. So that's like a bumpy driving, but the noise is high, right? So how would we decide? Oh, that is a constant velocity. Constant acceleration means, so you won't accelerate. You're going from 40 to 60, you won't accelerate. Did you talk about IMM?
Yes, I am just introduction.
Okay, yeah, but anyway.
Velocity model and its equation also.
Okay. So that is constant
You
acceleration.
derived also. How you that derived?
Okay, you do right. Okay.
Yeah.
So constant acceleration is there. Other one is constant turn. For example, flight is going, then it's turning in the constant turn and follow. Now you have to decide. Okay, you guys talked about IMM. Even like all my students, they know what is IMM, what are the models. But if I give a real world problem, they don't know how to tackle that. Because when they simulate, they do. Like that is why the academic industry people don't like our academic people because we make so many assumption, approximation, and so on, right? But how would you decide what model to use? Okay, as the first thing that you have to decide what kind of, it's nothing to do with the sensor. When you decide the motion model, it's nothing to do with the sensor. It depends on the scenario. When I say scenario, if you know that I am tracking using a radar for self-driving, then I know that I am tracking vehicle and pedestrian. Then I know because if you wait, which one is easier, tracking vehicle or pedestrian? Not forget about tracking filtering point of view. Which one is easier problem? Tracking a vehicle or tracking a person?
Vehicle.
Why?
High velocity.
Hmm?
High velocity.
Okay. The person also has velocity, right? Well, vehicle has 60 kilometer per hour, person has 2 meter per second. Okay.
We may confuse with the stationary object.
Pardon?
Pedestrian may be confused with the stationary object.
Stationary object. Okay, you can say that. Assume there's no clutter or anything. Clean scenario. You remember what I meant clean scenario? That's a clean scenario. Okay. Clean scenario. Which one is easier problem for filtering? Vehicle or pedestrian? Still answer is pedestrian. Okay, pedestrian is hard. I want the reason why. Okay, let's say for both of them, vehicle and pedestrian, we use constant velocity model. So we decided that because that's an easier problem, easier way to write a code. If you write a code, then IMM is good, but it's harder to implement, right? Sometimes even I do a lazy shortcut, always use constant velocity. But anyway, so even if you use IMM, there are several problems. But let's assume use a constant velocity. So what is the challenge with the pedestrian compared to tracking a vehicle? So what is challenging in this equation? When you track a pedestrian, what is challenging over here? Unpredictable. How do you translate that statement into a mathematical equation? Process not, right? So there is going to be, if you use a constant velocity model, this has to be really high. Because pedestrian can go and turn sharply. That same thing with the drone as well. Honestly, because I said that we developed tracker for the DNA, but when it comes to the drone tracking, it's hard. Hard means you won't get the benefit of Kalman filter. If you think about Kalman filter gives a benefit. The idea of Kalman filter is this, right? Simple filter anybody can do is connecting the measurement. This is a simple filter, right? Kalman filter, what it does is it tries to follow the middle. That's the idea of Kalman filter, right? But in the pedestrian tracking, if you increase the value of Q, then the black will approach the red. Okay, that's what's going to happen. Right? So when you increase the large process noise, you are losing the benefit of Kalman filter. Or the prayer is not giving anything. The idea of Kalman filter is that if you know the state, even before you get measurement, you know more about that particular location. But with the larger noise, you can't say much about it. So that way you are losing the benefit of the prayer. So that's why it's harder the drone and pedestrian because they are going to make high maneuver. Okay. So that is why, but again, like we didn't study about this, but let's say anybody can think about it. Again, as a testing of the knowledge of Kalman filter. So one person use a Q, it's a matrix, a vector, and I just simplify, say 1, Q2 is 0.1 and Q3 is 10. These are the 3 different noise level. Like I asked 3 different students to implement a tracking for a certain problem. One person use 1, one person use 0.1, one person use 10. What do you say? Which one is better? 2 is better. Any other answer? I'm not asking you to simulate the data and do the tracking. I'm saying that I give the data, you do the tracking, right? That's a real world problem. I think most of you are from industry, and you know that, right? So the data comes from the radar. Radar is not going to say anything. So one answer is that this is the best choice for Q. Any other answer? Okay, I say that that is not the best choice. Okay, go ahead.
It's based on the trust on the sensors.
Pardon?
Based on the trust on the sensor. Say, on the process model that you have.
I again repeat that the process noise nothing to do with the sensor. Okay, so process noise not connected to the sensor. You don't when you define that. When you define that, you never think about the sensor that you are using. It's nothing to do with the sensor. It's only to attach the target. Okay.
Who is the clean part?
Because these are the real world challenges. Because I can feel as an academic person, but then industry you can't use it. And also we write lots of papers like that. And if you want to translate to the real world system, you have to do a lot after that. Right? So even if you take any simple tracker, it will not work immediately. Oh, it will work, but for us, okay, our objective is to reduce the RMSE. But the real world people, that is not the only concern, like keeping the track consistently. I'm okay to have little large error. I don't want to break the tracks. I don't want to force track. There are several things to consider, right? So, okay, one answer is there. Any other answer? Pardon? 1. Okay, so that is the second answer. I say that is also wrong. Okay. Any other answer? Only remaining answer is the third one, right? I say that is also wrong. Okay. So because there's no optimal Q, right? How do you decide, right? So that is like because like before I joined as a faculty, I was working more long a lot of time as a research associate. At that time, I was posting a lot of real data. I develop a tracker, I keep the tracker, but always play with the parameters. Whenever I get a new tracker, new data, I always tune this parameter until I get a better performance. That is where you spend more time on that. But how do we pick a Q that reasonable? Usually, first you have to think about because I said 1.110. These are relative numbers, right? So you don't say 1 and 0.1 as a reason. First, you have to think about the unit. What is the unit of that? Say, for example, meter per second or meter per second squared, whatever the acceleration is, right? So you have to think about the type of the target that you track, right? See, if the relative and see if it's a vehicle, maybe this might be okay. For the person, it might be go here or there. So depending on the target type, you want to go deep. Okay. Okay, so let's say you are going to do the simulation. You do the simulation with 1, but in the tracker or filter you use 0.1. What will happen? Do you understand the question? So when you, this is a simulation, not the real data. When you simulate, you use this noise and generate the data. In the actual filter, when you use a Kalman filter, use this 0.1. Because like in the papers, we always match these two and you know that because you are the one doing it. Right? But let's say there's a mismatch. This is called mismatch. Actual is that and use this. What will happen?
Optimistic performance.
Or optimistic performance. Okay, can you elaborate on that?
Once the tracker will be less, so the performance will be much better as compared to what it should be here. Or better than variable.
What is the meaning of optimistic? Optimistic means the actual covariance is 10, but you are saying 6.
Yes.
So, or for example, a student is B plus student and say that I'm an A plus student. That is optimistic, right? You are saying you felt better than what you actually know, right? So that is a kind of optimistic. And the tracker says my error is small, but actual error is large. That's optimistic. That is not a good thing, right? So if you say that if I simulate the target at 1 and 0.1, I will get a better error, is that correct? Yeah, the covariance, yes, instead of that, you will get this. But in terms of the tracking error, you won't get it. Okay? But anyway, so if you study only filtering. With filtering, when you do this, errors might not be accurate, and I can't say that the estimate is going to be better. But in terms of the tracking, it's going to be a serious problem. Okay, so I'm talking about tracking instead of filtering. When we do tracking, if the target goes like that, if it goes, use a lower noise, then this is what will happen. So if the track is like this, and it might goes like that, but the measurements might go this way. Okay, this is called track law. Track comes here, and the measurement goes somewhere, then your prediction goes somewhere. So the data association point of view, you think that you are somewhere here, but the measurement is coming here, then you think that this is not coming from this target. True target, I didn't show the true target, but okay, you say maybe you think that the true is like this. Right? True is going like that. Wait, electron, so you asked about data association, right? So what we do is, this is the state at k equal to 1. Then you predict to k equal to 2. When you predict, it becomes larger covariance. That's the predicted covariance in the Kalman filter. But if the measurement is somewhere here, you will not associate. But if the measurement is here, you would associate. With the smaller q, what happened is that you are optimistic. That means you think that you are smaller, but the measurement falls there, but actually that comes from there. But since you are optimistic, you are ignoring that measurement, that you are going to lose that measurement. Then you are going to go with your prediction, then you lose the track. Right? That is a serious problem of using a less process on. So, but nobody knows the exact value, right? So even if it is 1, if you use 1.5, I am happy to go with 1.5 instead of using 0.5. Okay. So in the real world point of view, having a little larger process noise is better in terms of tracking in terms of 0.5. Okay, if you think about filtering point of view, 1 is always better than 1.5. You will get the optimal RMSE, but you don't know the exact value. So it's always okay to be a little pessimistic. You're not optimistic in the process. So, but this itself, theoretically, is not too much difficult, but in the practice, this is a harder problem. What model to use, what process noise to use, and so on. Okay, so when you work on a real system, please think about that.
Here, we are giving weightage to the state equation or the model. that
So,
we have.
yeah, okay, the karma filter is the weight, you give a weight between your prayer and the measurement, right? So prayer says I'm here, measurement say I'm here. So if I give more weight to the measurement, I estimate will be here. But if I give more weight to the prayer, then it will be somewhere here. So when you have a smaller process noise, you give little more weight towards the prayer, right? You trust the prayer more compared to the measurement, correct? But if the exact noise is known, you always go with that. But I'm saying that if you can tune that, basically you are saying whether to go with the measurement or not. That's what I said. If you increase the Q, if you increase the Q to a certain kind of infinity, that means the weight for the prayer is 0. Weight for the measurement is 1. If the Q is almost 0, at the steady state, or steady state, whatever it is, you always give the weight to the prayer compared to the measurement after some point.
Are there methods where we can adapt the Q value? Like based on the data that we are getting.
Yes, okay, that's a good point, right? So the idea of machine learning, okay, say these days everybody works on the machine learning. Idea of machine learning might be to get the Q from the data itself. And also the other problem is the Q is not constant, right? In all our papers and algorithm karma filter, we are saying Q is constant. Q is not actually constant, it can also time vary. But in the karma filter, always, yeah, we have a QK, but we consider that we drop the K after some point. But the Q fluctuates. Even if you are driving, maybe you are in a good mood and you go better. After some point, you change your driving habit for certain situation. So the Q might vary a little bit slowly. That way, so maybe you can be adaptive on that. So you run a different filter or different machine learning algorithm that can extract the Q from it.
But when I was developing track, I Q1 value, Q1, there's some value, it manually is to do. Then I got that, why can't I write an optimization algorithm so that I can optimally decide Q? How's that not done?
Yeah, you can think, but it's not an easy problem. I can't simply like say that, but it's not an easy problem to find the optimal Q. Okay, I can say that, right? So with the one data, like you are going to learn from the same data. Sometimes you might be biased the way you learn. That might introduce error. Sometimes it's always better. It might be better to go with some assumed constant noise covariant instead of adaptively estimating. Your estimate is bad, right? So you have to be careful about that. Okay.
Is there any thumb rule like personal that we should take? Any thumb rule like what's the range?
Oh yeah, okay. Okay, I'll talk about that. Okay, I'll come back to that. Okay, so when we talk about the tracking, these are the main things. Hopefully, I can cover that tomorrow. So tracking initialization, that's the first step. How do you initialize a track? In the Karman filter, we assume already track is initialized. But in this case, we don't know how the track is initialized. So the track initialization means how do you define that? At the first time. Okay, I will talk about that. So based on the measurement, how do you decide the initial state and the corresponding covariance from the measurement? That's called track initialization. So how do you initialize the track? Data association means like once you associate, already have a track. So data association means, so you already have a track, it goes like this, and you predict here, and you have few measurements here, here, and here. And then out of these 3 black one, which one comes from this target? Right? See, let's see, I do there. This is a data association. Associating the measurements to the track. That's a data association. Then the filtering. Once you do that, once you decide that this is coming from there, then tracking problem becomes a filtering problem. Okay. So after that, this is simply using a karma filter or an extended karma, whatever filter to update the state. Okay. Then the final one, track maintenance. I think we talk about track status, right? Tentative, confirm, and so on. how to update that. I will talk about that in the next.
So. And by set based on random set status. Eliminates the data.
Yeah, there are some simple. Sometimes they are call it a random penicillin. I'm not a big fan of random penicillin, but I don't use that much. But people call that we don't need the data association. But internally, somehow you have to have a data association. And there are some other algorithms like PDA in which instead of making hard data association, you say that 0.8 probability that and 0.2 probability this. Let's probabilistically say that, okay, most likely this and this. PDA, but I don't think we'll have time to talk about PDA here, but that's one example.
What is the promote?
Pardon?
What is the track promote?
Track. This one, maintenance?
Maintenance promote.
Okay. Again, I will talk about that in the next class, but anyway, quickly I will tell you that. So the track status, we talk about three statuses like that, right? Tentative, confirmed, this is dead. These are the three statuses of any track can have. Is that right? We all tentative, confirm, and dead. The user get only this. User will see only the confirmant. These are internal. These are the I don't know, you know about Markov chain. This is the way it can go. Okay. So this is called promotion. Going from tentative confirms the promotion. Okay. And these are like termination. This is the flow of a status. So a track status can go from tentative to confirm to dead. Is that clear? We'll talk about like logic based and quality based, how to move from one to the other. But idea is that we don't have that. We never allow that. We means maybe you can say I, but like sometimes people might do that, but I would say 99 or 95 or 90% of the people don't allow that. Don't allow this. I don't allow that. Okay, at least in my practice, I don't allow. So once it's that you can't go back to the confirm. So you start a new track, for example. Even if you lose an actual target, instead of going back and say that, oh no, I accidentally deleted. I said I deleted, that's gone. I will start a new track.
New ID.
New ID. Okay. Okay, this one simply talk about the flow chart, but those are the main steps. But once if you think about tracker, first you initialize the parameters. If you write a code, please don't hard code anything. Maybe I will show a sample parameter tomorrow. Initialize a variable. Then use the Monte Carlo only for the simulation. Okay. If you are doing a simulation and writing a paper, you have to have at least 100 Monte Carlos when you report the result. If somebody report the results based on single run, then definitely rejection for the paper, right? So nobody likes that, right? But in the real data, that is not there. So M is always 1. Then you generate a measurement and pre-process. Don't worry about that. We will do the tracking and then display and so on. Okay, I'm not going to talk too much here because I think you guys already talked about this. That's a concern velocity model, or nearly concern velocity model, in which this noise is in acceleration. Okay. So when we talk about concern velocity model, the noise comes in terms of the acceleration. And so you multiply by this to generate the noise. And okay, there was a question about what is the default process noise that you can assume. Usually I go this way. So assume the process noise in one direction, X and Y, is going to be some factor. Usually I make this factor as like like a fixed value, and I change this A max based on the target type. So if a car, A max could be like say 2 meter per second square. That is the acceleration and the noise level, right? So then you will say if the target can make that kind of acceleration, then the noise can be a factor of that. Okay, so based on the target type and how whenever that can be, then use a certain factor of that to do the process noise. That's what usually I pick the process noise for normal traffic. Okay. Okay, one quick thing I want to talk about this here on the process noise. If you use a CV, I have seen some students do this, that is wrong. Okay. So if you do this, say assume the model is like this and the VK is this with this covariance and this and generate the noise. You generate a random noise from this covariance. This is wrong. Okay, that is wrong. Can anybody tell me why that is wrong? Then the karma beta will not help you to do anything much. So we are now talking about a constant velocity model. And somebody developed the modeling like that. I teach this every time in the class, but I see that always one or two students finally end up with that. The reason is that if you understand exactly how the ensemble, because these are the pretty basic things, but that's important. Like if you make a mistake here, then you can't debug and find out exactly why the problem is on your code or the algorithm, right? The reason is that in the constant velocity model, if you see this carefully, this noise is the acceleration in the exponent value. Okay, say that is some value like 0.3. Then you multiply by this g value. That way you get the error in the x and error in the x dot. Okay, so you have a noise in the acceleration, and when you multiply e, you get this error part. These two are correlated. You see that because you can't simply move the x in one direction and x dot in the other direction arbitrarily. This is what happens if you do this. These are independent, right? You generate a random number for the error in the x, 0.3, and you generate a random number for the velocity in the error in the velocity is a negative 0.6. This will not happen in the constant velocity model. These two are coupled, right? If the error is this, so that error should be hidden. Because that's how the constant acceleration model works, right? So that is where you have to be careful, don't make this mistake. Okay, so always generate the noise for an x and then multiply by e, then that and okay. Then this is an acceleration model similar to the constant velocity model. I don't want to spend too much time. You can read more on that. So x dot, x double dot, then it comes to this one. Okay. And other popular model is constant turn. Again, I am not going to go through the equation in which the state content x dot y dot and this omega. Usually this omega is unknown for us. We have to estimate that as well. Usually this goes with an IMM model. So if you use IMM, one of them could be constant velocity, other one could be constant turn. Then you will try to figure it out which model is active at a certain point. So you can go like this and this way and that. So the tracker will automatically decide which is happening when. Okay? And then you follow it. Because I mostly want to talk about the real world challenges rather, and these are like, I think mathematical equation you can follow, right? Next, we are going to talk about the sensor type and that. Before that, I want to talk about one important problem, a practical problem, right? So most of the time we say X and Y as a state. How do you decide that state, what that you want to use? Let's say the radar is R and theta. So you want to do the tracking. Okay? So one person do this in X dot, Y dot as a state, and another person is using R dot theta dot. Okay. In this case, I am using EKF. Did you guys talk about EKF?
Yes.
Okay. So here I want to use karma filter. The next thing I will I think surely we will talk about this. You convert this into X and Y. Then you use X dot, Y dot. Then you give it to karma filter. Do you understand three options that we have? Radar gives R and theta. Now you want to use conditional velocity model. You have to decide the approach that you want to have. In one case, I have X dot, Y dot. Use a EK because it's a nonlinear measurement model equation. We can't use karma filter. Pardon?
Measurement contains R dot also.
R dot is a little complicated, but still you can add R dot, right? So I'm not going to talk that for now. Forget about the R dot for now. The no Doppler information that there. One option is to go X dot, Y dot EK. Another option might be R dot theta dot karma filter. Another approach is you know R and theta. I will show the equation. You can convert to X and Y. Usually R cos theta plus R sin theta, you get it. Then you use an X dot, Y dot and karma filter. And you know that karma filter is optimal. Right? Karma filter is optimal. This is suboptimal. Right? Which approach would you pick and which one is better?
I prefer to second one.
Second one, okay. Okay, let we talk about it. Answer reasons be after that. One answer is second one. Any other answer? Third one? Any other answer? I believe you understand at least the question, right? No, I don't, even if you don't answer, I think as long as you understand the question, that's fine. Pick something like because everyone is wrong anyway, so you can be wrong as well. Okay. Can you explain that? That is not going to be right. So the radar is going to radar is always going to give range and angle as much, right? So that will not change. I don't think that will decide which one to go with, right? The radar is always new. Okay, say if I have the radar, I measure the range and I measure the angle. Okay, you are here. That's what radar says, right? Okay, which one is optimal, right? Rather than going with the best one, which is the optimal solution? Because you know that EKF or uncentered Kalman beta, particle beta are not optimal. When it comes to nonlinear, it's always suboptimal, right? So in this case, which one is optimal approach? Second one, okay. How about the third one? Why third one is not an optimal one?
Third one, R data contains measurement models, which is Gaussian. So when I'm translating to X-ray, the noise model is changed.
That's right, yeah.
So I cannot use KM.
You can't use KF.
KF is not optimal then.
Okay, that's right. Okay, so in this case, okay, if you ask me which one is your optimal or which one do you, I personally prefer the, I say prefer, okay, I say prefer rather than anything else. I personally prefer that last approach. But none of them is optimal here. Because the problem is not linear problem, you can't solve it optimally. Okay, so this is not optimal. We know that EKF is not right. So what are the problem with these two? Like, okay, I will elaborate what she said. She said was the exact reason. This is not optimal. So this is a common filter, but we make some approximation somewhere. That's why we lose the optimality, right? The reason is that exactly what she said was that R and theta, that's a Gaussian noise. Now, when we convert it into x and y, you are converting R and theta into x and y. Maybe this conversion might become like this. Okay, the error is not actually, if it is a Gaussian, it has to be like this. Okay, let's say it has to be like that. But when you do R and theta to xy, sometimes it could. Then we are going to approximate this red with the Gaussian distribution in the converted machine. Okay, due to that, when we convert R and theta to xy, this Gaussian, then we approximate with the Gaussian, even though this translation bring into a different noise. So we lose optimality at that point. After that, we lose it. Okay, but this approximation might be not too much in most applications. That's why I prefer. But theoretically, I can't say that that's always optimal, and some cases that could be bad. Okay. Okay, now come to this one. Why don't you like that? That is optimal everywhere. This is a main topic. Mahendra will talk about this, right? So this is why. What is wrong here? Because everything is optimal here, right? No approximation at this point. What is wrong with it? The challenge here is the content velocity model. So you are saying target moves in the constant velocity in x dot, y dot. In the other one, you say r dot, theta dot. This is not correct. Target, this means that the angle is moving constantly. That will not happen. If you think about the real target, if the sensor is here, target might comes like that. That is not going to change the angle constantly or the range constantly, right? So the problem, people use that. I don't say this is completely wrong. I say that this doesn't have much physical meaning when you think about actual target, right? So actual target will not make a constant velocity movement in the polar coordinate. Actual target will have a constant velocity motion in the state coordinate and actual the world coordinate. Okay, so this is the problem. We can do it and you will get reasonable results, but that is not realistic. If the target is far away from you, it's okay a little bit. But if it comes closer to you, this is pretty bad. So the angle will change sharply, and if you plot the actual angle versus time, if it's a constant, it should be like that. But it might be most of the time like this or that. So that way it's not constant velocity in the angle. Okay?
Target is stationary. Just taking a turn. That means its theta is getting changed. Target position remains the same. Theta is getting changed after one week. So that this will.
So you are saying that
And then they would.
So your objective is to track the weight, right? So whether you want to vector vehicle in the world coordinate or your platform coordinate, I think the way you are saying you want to track in the platform coordinate, right? Right. So if you want to track in your platform coordinate, the vehicle is stationary, the target is stationary, and you are tracking there. Still, I don't say you can't use it. You can, but still, it may not be like always constant. Like if you make a turn, depends on your maneuver, right? So you go straight or you take turn, but the angle is going to vary because it's independent of the target. Your maneuvers will decide that, and in my opinion, again, that won't be like the straight line, right? So that is why I don't like this idea. So anyway, if you're interested in this talk, I believe another Dr. Mahendra Malik is planning to visit India, and that he's an expert on angle only tracking, and he came to McMaster last year, this year actually, 2-3 months ago, and he talked about this and main topic at it. And if you talk about say that you're using this, he'll be angry with you, right? So he doesn't like that. But anyway, so that's it. But it comes to the, like, if you want to implement an algorithm, there's nothing wrong with that. Okay? It's not accurate or not great, that's all I can say, but it works in most applications, right? You will get it. Okay? Right. Okay, last thing before we go to the next one. The real world is not X and what is X and Y? So I want to track ships. What is X? What is Y? Hmm? Pardon? Yes. So right. So if you have a real world, should be latitude and longitude. Right. So in the map, you want to track in lat long. So what is your state? Is it lat long or is it XY? It cannot be lat long. Okay, you can't do tracking in lat long because the motions are not in lat long. But the real world is lat long. What is your state then? What is XY? So in the real world also, even if you're tracking in the lat long, state is going to be X and Y by meters. What is that? Sensor origin? Okay, so one thing that you can do is you define the origin here, I would say lat 0 and longitude 0. So you define origin somewhere. Say if you want to track everything around Patna, so this IIT campus is 00. That location is the 00 point. Then what is X? You can consider that east. And this is north. Correct? But it's not stopping here. Okay? This is again a harder topic. Oh, you won't see much papers on that. But when you come to the real world, this is a challenge. Okay? So the challenge here is that what happens if the platform moves? Right? So you said sensor, right? The platform moves. Usually platform like aircraft, say you have radar on aircraft, it moves. So that's okay. That is okay. So I say this is the location of Patna University, but our sensor is somewhere here on an aircraft that moves. Then you convert that location to this. That's fine. You can do everything and do the tracking from that. Okay. But the main challenge comes for a autonomous vehicle or short range. This is not a problem. Short range means that if you have 2-3 kilometers, this is not a problem. But if you have a military radar in which it can have 300 kilometers, or it's an OTA radar, in which case it can be 2000 kilometers. You know about clutter, right? We assume Earth is flat. That is okay for that, not okay for this kind of thing. Then if the actual, if the aircraft is flying, if you are going aircraft flying at height of altitude, rather than height, I would say altitude of 10 kilometers. But if you have a origin somewhere here, and if the height is something like that, but because of the earth, it goes something like that, you will go here. Okay? And if you keep the origin always here, after some point, your height becomes somewhere less than 10,000, and it creates problems after some point. Again, so I say that I'm not going to talk too much about that because this is more details needed, but I ask you to think. What I do is, in order to handle this, I don't keep one origin. How many of you know AIS, autonomous AIS for ship? Are you on it? Ship will report their own location, automatic identification system, right? Say I want to track all the ship in the whole world. Then where is the origin? Right? You have to pick an origin somewhere. Then the approximation is not valid anymore, right? So what I usually do is, when I create a track, I will go back to this. Here, I will add another one called origin. Each track I will have different origin. And I will change this origin as well. I will not keep this origin fixed. I will keep this origin so that the height estimate, the flat earth assumption will not affect much. Okay, you have to do that properly, but I'm saying that if you are tracking a system in which the whole range is more than 300, 400 kilometers, then you have to worry about the flat earth assumption. Then you have to have an origin for each target, each track, rather than the one origin for the whole system. You will have an origin for each track separately. Then when you have a sensor that has different origin, you will come to the same, you will convert to the common coordinate, then you do the tracking of this. This is advanced, okay? You don't need to, even if you don't understand, I'm fine with that. But keep in mind that when you talk about the tracking a longer distance object, flat earth assumption effect, so you have to think about origin. Okay, that's all you need to take at this point. Okay, now we are going to talk about the measurement types and what are the measurement types have and how to use them. One is the linear measurements, like they provide X and Y. Not many sensors that provide X and Y, but there are so many papers that assume that. One sensor you can think that provides this is the camera. Camera is one example in which you can give X and Y. Or if the radar you convert to X and Y and use it, you can consider as linear, but otherwise, most of the time, you are going to go with this. Monostatic means transmitter and receiver at the same point. That is called monostatic. Okay. Radar means it sends a signal, wait until it comes back and process. So in this case, both at the same point, that's called monostatic. Multistatic means that's again radar with, for example, transmitter here, target here, so the reflection goes here, comes back. That is called bistatic or monostatic, multistatic, in which the transmitter and receivers are not at the same point. Okay, clear? That is called multistatic, or sometimes we call that bistatic. Bistatic means only one pair of transmitters and receiver. Multistatic means multiple pairs of lines. So you have one transmitter, you may have another receiver here as well, or you can have multiple pairs of transmitters and receivers. Okay. Other one is a bearing only sensor. There are so many cases in which you have only bearing only for even the sonar boats tracking, the submarine tracking. You want to do passive. You don't want the enemy to decide where you are. So most of the time we go with the passive sonar, but it might be cheaper as well. So that will listen for the sound and say something is in this direction. That's the angle only. But in terms of tracking, this is a harder problem. Okay. I hate handling angle. I can say that, right? because that's a hard problem to work with. Other one is the range state information. That's the topology we're talking about, right?
Multiple sensors, then it is a harder problem.
No, so like, yeah. So if it's a single bearing only, observability is the challenge. Like with a single bearing only, most of the time it's not an observed problem. Okay. But if it's a multiple sensors, the observed problem, we can do that, but still challenges there, but it's not that as bad as single angle only, right? But most of the time we go with the multiple angle on sensors, but it's tedious. Okay, the work process is tedious. Okay, you have to do the triangulation and data association and so on.
In that topic, like association for bearing only multiple sensors.
I won't talk too much in detail, but I have one slide I think talks on that. If you want, we can discuss more. Okay.
You're going to talk about.
Right, I have equation and talk about. Okay. So this is X, Y, Z, that you know that's straightforward. Okay, so then range measurement. This is the defining HX, right? So when you do a Karnaugh filter, you have to define HX. So this is a 3D problem. If it's a 2D problem, you remove it. Okay. But I didn't talk about elevation. In another case, we have elevation as well. Okay. Elevation. Bearing is the angle in the horizontal direction. Elevation in the angle in the vertical direction. Right. So the radars. Earlier we talked about when we use 2D versus 3D. We said that if we track ships, we use 3D. If we track aircraft, we use 3D. Let's say that we have 2D radar and 3D radar. 2D radar means R and theta. 3D radar means R, theta, gamma. Are you okay with that? So now let's say I want to track aircraft. I want to track aircraft with 2D radar. Which coordinate would you use? 2D coordinates or 3D coordinates? You understand the question? I want to track aircraft, but I have only 2D radar because that's the most case, I think. Like there are some 3D radars, but mostly widely used is a 2D radar. Okay? So if you have a 2D radar, you want to track aircraft, which one would you pick? 3D coordinate or 2D coordinate? 2D. You can do it 3D, but that is not observed. With single 2D radar. If you have another 2D radar, then you can do in 3D tracking and you can estimate the height. But if you have only one 2D radar, the height is not observed. Okay, so in that case, you would again use with the you would do the tracking in 2D. Okay,
For 2 radars are there,
then you can estimate the height.
both are giving one decimal target.
Hmm.
How do I get it?
Okay, can somebody answer to this question? The question is this. I said that if I have two 2D radar, I said I would use x dot, y dot, and z dot. The question is, how do we estimate this from this? You don't directly estimate it. We don't care about elevation. The question is, if I said that if you have one 2D radar, this is not observed. Now I say that if you have two, like this is observed, right? How? That's what he's asking. Okay, let's forget about the case. We'll come to this point. Okay. Now, what is going to happen in this case? So you want to do the 2D radar. So this equation is used in two different. Say, as in the simulation, this equation is used in two different places. One to generate the measurement. Other one is in the Karnaugh filter. Right? When you generate the measurement, you don't want to remove this. You want to keep this. But when you do the Karnaugh filter, you are going to remove that because your state doesn't have. Okay. Due to that, what will happen? So your radar is here, target is here, ideally somewhere here. If you do the tracking in this case, where will you be at, you estimate? Here or here or here? 1, 2, 3. What do you think? Anyone? I use a 2D radar and I use it, and this is the actual height of the target. If you do the tracking, your track output will be at position 1, 2, 3. This is 3D and this is a 2D projection, right? Where will it be? 3. Is that right? Because the projected range, right? So actual range is there. So estimate will be here, right? Now, if you have another radar on other side, let me go again here. So if you have here and here, this projection will go here. And if you have another radar here, that projection goes here. You understand that? That is where you get the information about the height, right? So this is a simple explanation of that. So because of that, you know where intersect in the 3D world, right? They intersect at that point. So that way it comes up. Okay. Okay, and then the angle here, the angle is A tan. Again, the one thing that you need to notice A tan is MATLAB has two functions. A tan 2. Which one would you use? You have to use A tan 2. Okay, not A tan. Okay, you have to be careful about that. Okay. And the other thing, anyway, I don't think I will have time. I will talk about that in some other places. But if you're using EKF, you have to be careful when the target, say your sensor is here, target is moving exactly on this line, then it's going to be a problem. Okay, you can't, because your angle could be here and here, and if you subtract, the error becomes like 2 pi, close to that. So that is a problem. Okay, so when this is, the problem is this is minus, this is plus pi, this is minus pi. But the difference is small. Actual difference is around maybe 0.001 degree, 1 radians. But the way we do the difference, it becomes almost 2 pi radian. Okay, you have to factor that properly when you do the harvest. Okay, keep that in mind. Okay, this one talks about, because even in the assignment, this is what we are going to do. Conversion. Okay, the approach I am going to solve is to do the conversion. So you are given R and theta and corresponding R. Because usually that's like sigma R squared, 0, 0, sigma theta squared. So you want to convert into X and Y. And this is, you can call it an R bar. That is the RXX, RXY, RYX, RYY. Okay. So this is diagram 0, 0 here. But when we do the conversion, you will have non-zero values here. Okay. So what happened is that in the R and theta coordinate goes like that. If it is XY, it might be something like that. Okay. So we do the conversion of the coordinates and then goes there. Simple conversion is then X equal to X sensor plus R cos theta, X Y sensor plus R sin theta. Correct? So if you have sensor somewhere, so that the converter measurement is a sensor location plus this. And so that is what we have here. So if you do that conversion, so this is a conversion line. I don't have, you may need to add Y sensor plus and X sensor plus. Okay? You do that conversion and get it. But if it's a real problem, the real world, and you are developing algorithm, you can go with that. But if you're writing papers, if you want to do properly, people have shown that if you do the conversion like this, okay, if you do the conversion like this, actual target is here, okay, and your measurement is somewhere here, and say you generate 100 Monte Carlo run, and if you do the conversion using the equation that we have, the mean might be not same as actual target. This is called bias. Okay? So you have 100 measurement generated from the same target location. Target is not moving. You can convert that to this state coordinate using r cos theta or sin theta. If you find the mean, if it's an unbiased estimator, these two has to overlap exactly at the same point. But they have shown that they will not overlap, so that conversion has some bias. Okay? So in order to remove that bias, so they have shown that the bias is this part, that is this. In order to compensate that bias, basically they multiply by B inverse here. So B inverse is this. Okay. So if you want to use that proper way of conversion, so you want to multiply it by B inverse. That is a function of the measurement forward, measurement standard deviation. That is it. Okay. Okay, so please go through the math, because my idea is to give a high level view so that you can go and read more on the exact detail. Then the corresponding covariance, because I said you need to have R11, R22, R22, R12. Sorry. Wrong. R12, R12, R22. Okay? R21, yeah, okay, so R21 and R12 are the same because the covariance matrix, so symmetric, so that's fine, right? So the equations, I'm not going to worry too much about the equation, you just plug in and you get it. So when, like in the next class, in the tomorrow, when we talk about factor initialization, this is the covariance matrix that we use to initialize. Even if you don't, even if somebody is going to use, I said we can do two approaches, right? R theta, convert to XY, then use Kalman filter. Kalman filter, or you can directly use EKF. Even if you use this, even if you go this route, this conversion is needed for track initialization. So in order to initialize the track, you need to convert all the measurement to XY. Whether you use a 100 measurement Kalman filter or EKF, this is what we are going to do. Anyway, I will introduce it to them as well. Maybe in the quiz also we may have something like that. Even the assignment I have. So I have two terminology. One is C and KF. Other one is CKF. CKF. C and KF mean converted measurement Kalman theorem. So that means R theta is given. As the first thing you convert R theta to be X and Y, then use the Kalman filter. In the other case, you directly use R theta to use the EKF. But whichever algorithm you use, whether you use EKF or CNKF, you have to convert the measurement to R and theta to X, Y in order to initialize the track. So when you do the conversion, always you have to have the covariance as well.
Is there a methodology to do directly in the polar coordinates?
So that is one approach that we discussed, like having like R dot theta dot. I said I don't like it, so that's the answer, right? I don't like that, and I don't recommend you to do that. Okay, so better to converse and go do it never. Okay. Okay, then this is a little advanced stuff. I will skip it, but you can read. This is bistatic sense, in which transmitter is here and receiver is here, so it goes like that, right? So in that case, then the measurement equation for the range is R1 plus R2. Okay, so that R1 is the distance between the target and the receiver, distance between the target and the range, you add, that's a bistatic range. But the angle is always measured from the receiver. It doesn't worry about the transmitter at all. So that's why in the angle, we don't have the transmitter here. It's only measure the angle from the receiver. So that's the bistatic. Okay. Okay, range rate, I'm not going to talk too much about it, but this is the equation of range rate. If you think about police car, I don't know about India, they give a speeding ticket, right? So they give a speeding ticket, they use this information, right? They want to find out the range rate and how fast you are moving. That's the Doppler information. They give the speeding ticket based on that. So basically, range rate, if you are moving in this direction, for example, you are moving in this direction with 10 meters per second, and if your radar is somewhere here, that is not going to provide, in this case, R dot could be 0. Okay, R dot is the speed in this direction. So that means if you are traveling like this, police car is somewhere here, they can't give the speeding ticket. If they want to give the speeding ticket, they have to be here or here on the same road. Right? So that is the range rate. That is a limitation. When it comes to track initialization, I don't usually use the range rate because that is not fully observed, but still you can. So if you have somewhere here, then the measured range rate could be, for an example, say 6.2 meter per second. So that is the range rate in this time. That is, I told it measured. Okay. So it has information. It has definitely information. Similar to that, if the bistatic, then you have range rate from the receiver and transmitter, it comes here. Once you write its age, then it's come to the EQ, extended Kalman filter. Then you find the differentiation and use that in the normal filter. Okay. Okay, next comes to bearing voltage sensor. There are two types of bearing voltage. Again, 2D and 3D. 2D means theta, 3D means theta and gamma. Okay. So in one case, it says something on this direction, another one says in this direction as well. Right? That is the bearing only sensor. This observability is a problem with the angle only sensor. But under certain conditions, one angle only sensor is enough to do the tracking. For an example, this is a aircraft, it goes and you want this is ground, and you have an angle only sensor here. What do you think? Is it an observed problem or not? Object is here. Okay, before that, let's talk about that. This is a 2D problem. 2D problem. So your receiver is here, and you are saying something is here. Okay, do you think we can estimate the track? So you want to track a ship from another ship, the angle only measurement is here. Can you tell where the other actual target is? Anyone with the angle only? You said, is it possible or not? No, right? The range is not known. Even if you get multiple angles, it's not possible because it can move like that, it can move like that. Both will give the same answer. It's not observable, right? How do we make it observable? Pardon? Sure, right. So that's a little advanced stuff. To make it observable, you have to move the sensor something like that. Okay? If your sensor moves in a one order higher than the actual target, then because of this maneuver, the problem becomes observable. Okay? That's the case, usual case. Now I am talking about another case in which there's an aircraft, you have an angle only sensor, target is on the ground. Is it observable or not? No, target is moving, but it's on the ground. Target is not stationary, it's on the ground. Aircraft is moving on the top. So you want to find out that. Is it observable or do you need extra information to do it?
Wherein is obtained at the
Yeah. So you will assume you know the bearing and elevation from the aircraft. Observable. Reason?
Multiply. So.
Okay, so if I switch the problem, it's an observable. Angle on sensor is here, that is a target. First I said this is a platform. Platform means that where we have the sensors. Okay. So in one case, I said platform or the sensor is here, target is here on the ground. In the other case, sensor is here, target is there. Kind of similar problem or different problem? Similar problem. So that means you are saying that if the sensor is here, target is there. Is it observable problem? Can you estimate the target? No, you can't, because you don't know the height of the aircraft. Okay? You don't know the height of the aircraft, so height means altitude of the aircraft. So it's not observed, right? Because you know that only something is here, but you don't know the height. Now I switch the problem in which radar is on the aircraft, sorry, angular sensor is on the aircraft, target is on the ground. Is it observable or not?
Yes.
Okay, why?
It's high.
Yeah. So in the first case, target is the target. We can't get any information from the target, so height is not known. But in our case, the platform is ours. We know our altitude. So that information is there. Huh? Then this is the observable, right? But one of my students did one of the paper on this problem where terrain uncertainty. Like usually that's the real world versus the theoretical problem. In theory, you assume its height is fixed and ground is like one straight line. But that's not the case, right? The terrain has some uncertainty like 100 meter, 30 meter accuracy. Then this is not hard, easy, right? Easy problem. There are challenges with that. So that's what it says, right? Under certain circumstances, angle only sensor can work. This could be in satellite also, right? There are satellite based angle only sensors as well. Satellite based missile tracks, right? For an example, right? If you want to track missiles using a satellite with the angle only, is an observable problem. Still, the height is not known, but if your objective is not about exactly estimating the height, but you want to know whether it's in over the China or over the India, at least at that level, you can say that, right? With some projection error, but still it's observable, right? That's it. We almost end, and I will talk about a little bit of. I know that you guys have already talked about Kalman filter, but I just want to bring the measurement space and the state space, and we will use that in the data association. Okay. So I quickly talk about that so that when we talk about the data association, it becomes easy. So we have two state spaces. One is the state space. Other one is the measurement space. I always go with an example, right? So we will do the initially track initialization here. We will do the data association over here. Okay. Just to clarify that. So let's go with the Kalman filter. For the Kalman filter, these are the two inputs we start with. This and this, right? So we start with those input. If I convert that to this, I say that is somewhere here. Target is somewhere here. So in the first step, we do the prediction here and here. Where do we do that? Do we do that in the state space or measurement space? We do that in the state space. That's right. So we do that in the state space so that we move it somewhere here. Maybe the coordinates become larger. That's the state space. And what do we do here? We do the measurement prediction. Where do we do that? Do we do that in the state space or measurement space? That's not exactly correct. So usually we do the mapping from measurement state space to the measurement space. Is that right? Rather than doing in the measurement space, this is in the state space, this is in the measurement space, so we do the mapping. Correct? So we convert that and that's one. Both are the measurement space to the state space to the measurement space mapping. we do that over here. Okay, that is the mapping part. Okay, that is the going in the direction. And where this is the innovation that we calculate, right? So innovation, we calculate that. So it's here. So the measurement is somewhere here. So I find this gap. Where do we do that? That is in the measurement space. Okay. And then we do the update after that, right? So then we do the update that is in the state space. When based on this, we will go back and somewhere like that. That's final update that we get. Okay, that's a normal Kalma filter, but you need to know what is done in the state space and measurement space. What is the difference between the set space and measurement space? And whenever we do some data association others, mostly we will work on the measurement space. Even if we convert to XY, we are going to work on it. And also, please be familiar with the terminology. Like you know equations, but like when you talk to the Kalma filter, when you talk to somebody, you should know the terminology. Predicted state, that state that we get with the predictions. Predicted state covariance, predicted measurement, innovation. Like this is that like others are kind of intuitive. Innovation is not intuitive, but like people use that in papers many places you have it. Innovation is the gap between the predicted and actual, right? So please that innovation covariance that is there. Because this is the important part. When we do the data association, we will use this innovation covariance, right? So innovation covariance is the important part in deciding the data association part. Gain is the one that gives the weight between the prior and the measurements. By changing your covariances, the gain vary, and others you know that, right? Extended Kalma filter, I'm not going to talk too much about that, and we covered a little bit, and that's like, that's not much, I think you can just refer that, right? IMM is a monster, right? Like that is really useful, but you have to use that as well. And if you're using machine learning, there are so many new papers on machine learning as well for IMM deciding when to use which model and so on, right? Okay, that's all for my at least introduction. I would call as tracking, but like tomorrow, I think we will talk more on the performance evaluation part. That first I will talk about performance evaluation. Then we will talk about some how to do the tracking and so on. Okay. Any questions? Anyway, I'm able.
Assisted IMM is there.
ML assisted IMM. ML assisted IMM is there. ML based IMM is there, and so on, right?
Pressure is concerned.
Yes, yes. I have reviewed many papers on machine learning based IMM. But yes, but I from academia industry. So maybe you can wait. I think you don't need to worry too much about that for now, right? So the normal IMM might work, right? So machine learning IMM usually people go for like unknown mode, possible noise, and so on. But I would say usually I always go with constant velocity and constant turn, even though they are not optimal, but that's easier to work with. And because when you add more and more models, the performance won't be that great. So, I would say like you start with some model and do the tracking, and then if the performance is not satisfactory, first think about the CRLB. If you have enough room to improve, then think about machine learning or whatever alternative. But if you already reach the optimal or close to optimal, either you have to replace a sensor or add more sensors rather than picking on the. Okay, if you have more questions, you can talk offline or tomorrow. Okay, thanks.